And as xx, power spectral density function gives us the information in the frequency domain. Okay, so the time domain information is specified by the autocorrelation function. And in the frequency domain, it's specified in terms of the power spectral density for stationary random process. Okay, and then at the end of last week, we were looking at a few examples. And if we have a harmonic function, okay, so if x is a cosine omega 0 t plus some phi, it's a harmonic function. Okay, so it is definitely a deterministic. Now, if we treat it as a random process, the correlation function is a harmonic function. Okay, if you sketch xt, what the correlation function says is when the time difference is 0, it's perfectly correlated. Okay, so that's 1. The correlation is 1. And after a period, they are perfectly correlated. Okay, now after half a period, the correlation is -1. Okay, so that's -1. So you can see the correlation function is also a harmonic function, but it's independent of the phase angle. Okay, so when tau is 0, this point is fully correlated with itself. After one period, it is also fully correlated. Okay, and then that's also a harmonic function, the correlation function. After half a period, this value and this value are negatively correlated. Okay, with the correlation coefficient -1. Now, if we look at the frequency domain, because we only have one frequency component, omega 0, therefore the power spectral density function is the delta function at omega 0. We only have one frequency component. Okay, and then we have exponentially correlated random processes in the second diagram. In this case, the correlation function decays exponentially. Okay, so if alpha 1 is relatively small, the decay is relatively slow. Okay, and then we have frequency components focused within a small frequency band. Okay, within a small frequency band. So you can see here the blue curve. Okay, corresponds to a relatively flat correlation function. Okay, so that means the flatter the correlation function, the narrower the frequency band of the power spectral density. Now, for alpha 3, the decay of the correlation function is relatively sharp, but the corresponding power spectral density function is relatively flat. Okay, the power spectral density is relatively flat. Now, the third case is a limiting case of alpha 3. Okay, so when the frequency band is much wider, so it's a constant throughout the frequency range, this correlation function becomes narrower and narrower, and then the limiting case is a delta function. Okay, so if you have a delta correlated random process, then it has a very wide power spectral density. In the limiting case, it is a white noise process. That means the frequency contribution is constant for all frequency component. Okay, so you can see from a delta function for the frequency band, a power spectral density, it is a harmonic function. And when you make it wider, it becomes a narrow band frequency. For narrow band frequency, the correlation function is relatively flat. And when you increase the frequency band, the correlation becomes smaller. In the limiting case, when we have a white noise process, the correlation function becomes a delta function. Okay, and last time we explained why we call SXX power spectral density, because it is the expected value. It's related to expected value of x squared. And if x is a current or a voltage in an electrical circuit, x squared is related to power. It's I times V, it's power. Okay, so E x squared is the mean square value or the expected power, and it's related to this function, the power spectral density. So that's why Sx is the power spectral density function. Okay, these three diagrams are very important. Okay, if you understand them, you would be able to visualize a random process. Okay, the power spectral density of a white noise process is constant over all frequency. As shown in the diagram, a white noise process is clearly not physically realizable because its total power is infinity. However, it is a convenient mathematical idealization for a process whose power spectral density function remains practically constant over a wide band of frequency. Okay, later we will study under what circumstances can we model a wideband random process. Okay, so this is a wideband process. When can we model this? Approximated by a white noise process. Okay, we will study this later. The white noise process cannot be realized physically, so it's always an approximation. Okay, and under what circumstances can we approximate a process as a white noise process? Okay, we will study this later in the next chapter. Okay, power spectral density function as x is very important in characterizing a stationary random process. For transient non-stationary process, we cannot use power spectral density. Okay, the reason is power spectral density characterize the power. Okay, power is energy at a specific time, average energy at a specific time. Okay, for a non-stationary process, for example, earthquake, ground motion. Okay, it has a build-up phase, a strong motion phase, and a decaying phase. Okay, in this case, we cannot talk about the power at the time because the power at this time and the power at this time would be different. Okay, and then after some time, there's no power. So we can only talk about energy. In this case, we cannot use power spectral density. We introduce Fourier amplitude spectrum, FAS. Okay, so the Fourier amplitude spectrum is defined as this. We first find the Fourier transform of X. Okay, so this script X is the Fourier transform of the random process. And the absolute value of the Fourier transform is called Fourier amplitude spectrum. And X is the inverse Fourier transform of the script X. Okay, so here again, this is the time domain. Xt is in the time domain and x omega is in the frequency domain. Okay, so the total energy is integration of x squared with respect to t from minus infinity to plus infinity. And it's expressed in terms of the Fourier amplitude spectrum as this. Okay, so x omega squared is called energy spectral density function. Okay, let's look at the footnote first. It is appropriate to characterize a stationary process in terms of power, which is the energy in unit time, and power spectral density function. Okay, so because we are looking at energy in unit time, so as we look here, for this portion is fine. Okay, so you can talk about energy in this time, but it's different from what we have here and different from what we have here. Okay, so only for stationary process we can talk about power or energy in unit time. For transient non-stationary process, we can find the total energy. You can find the total energy for the process. Okay, through total energy, Fourier amplitude spectrum, or energy spectral density function. Okay, so E is the total energy. Absolute value of X is the Fourier amplitude spectrum, and the Fourier transformation absolute value and then squared gives us the energy spectral density function. Okay, now I want you to, this part is very abstract. I want you to give you a few minutes. Okay, give you a few minutes to do the following. Okay, so first, draw a harmonic function. And that should be easy. Okay, so the power spectral density function this is omega and SXX omega. Okay, so we have omega 0. So first draw this, and then you draw a narrow band process. Okay, so for narrow band process, we also have omega 0. Okay, should be symmetric. Okay, and then third, draw a wide band. Or you can draw a white noise process. Okay, so this doesn't matter that much. So we have quite flat power spectral density. Okay, I'll give you a few minutes, say 5 minutes, to draw the narrowband process and the wideband process. Okay, just from your what you know about random process, just try to draw realization of a narrowband process and wideband process. Okay, it's a very important be able to visualize a process, and when you see a process, you can identify, oh, this is probably wideband, and oh, this is a narrow band. Okay. I'll give you 5 minutes. Now it's 7:29, and think about it, and we will come back at sorry, 8:29. So we come back at 8:35. It's important for you to think about it first. Then I will explain to you how to visualize these random processes. Professor Tang，汤老师，
是你好，
您问问同学能不能画出来？
我叫他们到黑板画。
您有没有摄像头能看一下？Okay, thank you. Okay, so now the first one is very good. It's a harmonic function. It's a sine or cosine function. Now let's look at a narrow band process. Okay, for narrow band process, you can approximate it as it has obviously a frequency component omega 0, another frequency, okay, close to omega 0, and a few more. Okay, so we have frequency components omega 0, a little bit less than omega 0, some more than omega 0, and so on. Okay, so you can approximate this as having a few frequency components. Can we sketch this? Okay, so this is omega 0, this is omega 0 plus some more difference, delta omega. Okay, so we only have two components. Okay, so this narrow band would be similar to this, but with more frequency components. Okay, so obviously we know this. If we can draw this, then we should be able to extend to draw this. Okay, Professor Tang, please ask a student to draw this case. To draw this case, we have two frequency components close together.
哎，是啊，是刚才这个同学他把3个都画了。
对，要画一下这个。唐老师，请同学画一下这个情况。Draw this case. We have two frequency components, omega 0 and omega 0 plus delta omega. And these two frequency components are quite close. Let's look at this case first. And then we extend to narrowband process. Okay, to do this, we study a single degree of freedom system, undamped single degree of freedom system. Okay, so you have x double dot plus omega 0 squared. Omega 0 is the natural frequency of the system. Under harmonic excitation, so the excitation frequency is omega. We can solve the differential equation. We have the complementary solution, and it's a cosine omega 0 t plus b sine omega 0 t. Okay, and then the particular solution depends on sine omega t, the excitation, and then the denominator is this omega 0 squared minus omega squared. So when a capital omega is the same as omega 0, we have resonance. The denominator becomes 0. Okay, so now you plug in the initial conditions. X0 is x sub 0. the velocity at 0 is v0. Then the solution, after solving for the constants a and b, it's given by, the solution is these. Okay, the first two terms are the free vibration. The last term is forced vibration. Okay, so you can see it has sine omega 0 minus t minus sine omega t. Okay, so that's the term. It is a combination of two harmonic functions, sine omega 0 t and sine capital omega t. Okay, omega 0 is the natural frequency, big omega is the excitation frequency. So now we want to sketch this function. To sketch this function, we use a trig identity. Okay, so sine A minus sine B is 2 cosine A plus B over 2 sine A minus B over 2. Then you can get this. Okay, so we have two terms. One has this frequency, the other has this frequency. Okay, so now if omega 0, capital omega is close to omega 0, this is very small. And this is close to omega 0. Okay, so that's fine. So when frequency is small, we can consider the whole thing as the amplitude for this cosine function. Okay, so this is a cosine omega 0 t. It is this cosine function, or let's make it change fast. Okay, so this is cosine omega 0 t. But this term is with very low frequency. For very low frequency, okay, so this is a low frequency. This is, say, relatively high frequency, omega 0. Okay, is that clear? So now this whole term is the amplitude for the blue function. So we are fitting this blue cosine omega 0 t into the red amplitude. Okay, so this becomes the amplitude. Okay, now this is the amplitude. It has frequency omega 0 minus omega over 2, which is very low. Okay, and cosine omega 0 t has a higher frequency. Therefore, what we are plotting is we use this. As the frequency for the cosine omega 0 t. Okay, so you're basically fitting this function into here. Then we get the diagram here. Okay, so now next page, we have simulation. Okay, so I plot omega 0 is 1, capital omega is 0.95. Okay, so then omega 0 minus omega over 2 is 1 minus 0.95 over 2, so 0.025. Okay, so you can see the frequency is quite low. You have this. Okay, so now if you increase omega to 0.98, this is even smaller, so that's 0.01. And this is 0.005. Okay, so when you have two frequency components, you would have something like this, and it's called B. 中文叫做节拍. Okay, so if you have two frequencies very close, it looks like this. Okay, so if you have a sound, it goes wow, 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 wow. Okay, and in physics, this is called a beat. Okay, so now when the two frequencies are much closer, you have this. Okay, then it becomes even closer. Wow, wow. And then when you decrease the frequency difference, this becomes very large. When they are almost the same, we have our resonance. Okay, so the amplitude increase linearly. And so the resonance case is a special case of the beat phenomenon. Okay. Okay, so now this is the case when we have two very close frequency components. Okay, and the resulting process is a beat, or resulting function is a beat. Okay, so remember this is a beat. So for narrowband process, we have a envelope, okay? Because now it has a few frequency components. Okay, so the envelope, in this case, is not a sinusoidal function, but it changes. Maybe I draw a few more. Okay, so this is narrowband process. Okay, so it has an envelope. This is called an envelope, 或者叫做包络线。Okay, it has an envelope, and the envelope varies slowly. And then you have a sort of a cosine function, harmonic function inside. Okay, so this would be a typical realization of a narrow band process. Okay, is that clear? Okay, so now for a wideband process, it has 4 frequency components. Okay, so if you in the first drawing, the student I think he drew something like this, right? And this, you can decompose this into a low frequency component plus a high frequency component. Okay, so this is low frequency, and this is high frequency. And so this is not a wideband process. Okay, it is basically, it has 2 frequency components, a low frequency component and a high frequency component. Okay, so now how does a wideband process look like? It should have all frequency. Okay, so that's low, that's medium, and then out of medium you have a lot of these. So something like this would be a wideband process. Okay, I will show you in another simulation. Okay, so here I use MATLAB to generate Gaussian white noise process. We will talk about Gaussian process in a moment, but it's a white noise. So if it's a white noise and it's also Gaussian, then it looks like this. Okay, so this is a Gaussian white noise process. And so if you think about a wideband process, you can think about, visualize it as this. Okay, so it has lower frequency components, medium frequency components, and high frequency components. Okay, so even this you can, okay, so when you increase, you can see inside the medium frequency. So for example, this could be considered as medium frequency, okay? And then this would be this portion would something like this would be a higher frequency, okay, higher frequency. And then you have the, this would be lower or intermediate frequency, okay? So when you put everything together, something like this, okay? And then we can plot the Fourier amplitude spectrum. In this case, if you use very high frequency resolution, because of the resolution in simulation, you can see it's quite, it has a lot of variation. Now, if I decrease the frequency resolution to 0.02 Hertz, it's quite flat, okay? Now, if you decrease it further, then the Fourier amplitude spectrum is almost a straight line, okay? So that's how you visualize a wideband process using the Gaussian white noise process as a limiting case. Okay? Now we take a short break. Now it's 9:02. Please come back at 9:10. Okay, so 8 minutes break. The reason I go through all this is for you to be able to visualize a random process, okay? A random process is random, but in order to study a random process, we have to make some approximation. So in the frequency domain, we have a narrow band process and we have a wide band process, okay? A wide band process, the limiting case is a white noise. For a narrow band process, it has a central frequency and then some other frequency components close to this frequency. Okay. Mathematical model of a narrow band process is called bounded noise process. Okay, so here we have a cosine function, cosine nu t. If you only have cosine nu t, it's a harmonic function, okay? And we add a random phase angle. So angle theta is uniformly distributed random number between 0 and 2 pi. Okay, so without the middle term, we have cosine nu t plus theta. It's a harmonic function. Now we introduce this noise term, sigma times Wt. dWt dt is a Gaussian white noise process or unit. Gaussian white noise process. Okay, so sigma is the amplitude of the noise. Okay, so obviously when sigma is equal to 0, we have yt equal to cosine nu t plus theta, and this is a harmonic. Okay, we don't need to go through the derivation, but if you look at the correlation function, of this bounded noise process is given by this. Okay, so it has two parts. The first part is cosine nu t. Can you relate this to something else? To what we just studied? When sigma is 0, yt is a harmonic function. Okay, for harmonic function, the correlation function is also a harmonic function, cosine nu t. Okay, now the noise part, sigma wt, gives us this term. Okay, this term is a exponential correlation function, and that's what we studied here. Okay, correlation function is a exponential function. You see, the correlation function is an exponential function. Okay, so the larger the value of alpha, the narrower the correlation function, the wider the frequency band. Okay, so basically the bounded noise is the combination of a harmonic function and exponential, the correlation function. Okay, so when sigma is 0, we only have cosine. When we increase sigma, okay, we have exponential decay. Okay, so the larger the sigma, the more noise we have. Okay, so you can we can also derive the power spectral density of this bounded noise. Okay, so what we have is I sketched the power spectral density function here. And let's look at the case. Nu equal to 3. So we have central frequency around nu equal to 3. Sigma is 1. Okay, so when we increase sigma, it becomes flatter. Okay, so you can see for sigma small, it's quite close to nu equal to 3. Okay, so this is basically a narrow band. And when you increase sigma, nu equal to 3. So this becomes wider. Okay, so the frequency band becomes wider. Okay, so you can just visualize this. Okay, so that's a cosine, and when sigma is small, there's no noise. It's a pure cosine function. When we add noise, you would have other frequency components coming in. Then the bands, the frequency band becomes wider and wider, and it's a combination of cosine function with random process with exponentially decaying a correlation function. Okay. Okay, so take a minute to visualize a harmonic function, a narrowband process and a wideband process. Okay, and later this information would be quite useful. Although we cannot sketch some of these random processes accurately, at least you have a basic idea how they look like. Okay. We introduce another concept. It's called a ergodic random process. So far, we studied 2 averages. Okay, last week we studied 2 averages. One average is the ensemble average. We need to find the probability density function of the random process and then evaluate the expected value. Okay, and another thing we can do is use the time average. We take a typical realization xk and we just integrate for this realization and then divide by time t, okay? From 0 to t and then divide by t. This is called time average. Okay. In general, time average and ensemble average are different. For some special situations, they are the same. Okay, so obviously it's much easier to evaluate time average. Okay, so the average we have discussed so far are all for ensemble averages. Evaluation of such averages can be challenging, very difficult, because we need a very large number of sample functions. On the other hand, the time average over a particular record can be easily computed. Okay, it is then most desirable to know under what conditions the 2 types of averages are equal. A random process whose averages possess this property is said to be ergodic. So that means ensemble average is equal to time average. And if this is true, then the random process is called ergodic. Okay, so this is the definition of ergodic. In essence, ergodicity means that any particular sample function used to calculate the time averages can be expected to be typical of the whole sample. For a typical record xk of an ergodic random process, one has this property. Okay, so we can use the time average as the ensemble average, and then you can evaluate the correlation function using this formula. Okay, so now without looking at the next paragraph, I want you to visualize when is a random process ergodic. What kind of process would have ergodicity? What process would be a ergodic process? Okay, only when you are able to visualize such a process, you can reasonably use approximation. So you say, oh, this is a good approximation to approximate a process as an ergodic process. Then you can use time average as ensemble average. Okay, so how does a ergodic process look like? Okay, so it means any particular sample function would be expected to be typical of the whole sample. The whole sample means you have a number of realizations. Okay, you have a large number of realizations, and then for a specific time instance, it has a realization, and a realization. And then this is typical or similar to what you see for a typical sample. Okay, so if that's the case, the random process must be stationary. Okay, so because time average are independent of time, stationarity is a necessary condition for ergodicity. Okay, and the English name here is not very informative, and the Chinese translation is much more useful. That's called 个态力均. So you can ergodic process called 个态力均过程, or every state is visited. or you can say all states are visited. Okay, let me explain this. Suppose we have earthquake ground motion. As we mentioned before, we will study it in more detail later when we study earthquake engineering. It has a build-up phase, a strong motion phase, and then a decay phase. Okay, so you can break this into 3 phases. This is the build-up, and this is strong motion, and this is the die down or decaying phase. And then the earthquake would be something like this. Okay, so is this ergodic? Obviously not, because in the strong motion phase, it visits all the states. Okay, so from small to large. And in the build-up phase, especially let's say in this portion, you only have very small values. Okay, so the large states are not visited. Okay, and similarly, in the die down phase, the large states are not visited. So it is an earthquake ground motion process is not an ergodic process. Okay, so for a random process to be ergodic, it must be stationary. Okay, so if you remember, if it doesn't look like stationary, obviously it's not ergodic. Okay, and then you can use this to test. Are all possible states can be visited? Okay, so in this case, only the small states are visited. Okay, and only small states are visited in the build-up and the decaying phases. Only small states are visited, and for the strong motion phase, all the possible states are visited. Okay, so this portion can be modeled as stationary. We will study this later, so you can see from here, all the states, possible states are visited in the strong motion phase. Okay, so this portion can be approximated as stationary. If it's stationary, you can it also looks like ergodic. Okay, use this to test. All states are visited, because for physical processes, it's very difficult, very challenging to rigorously prove that all the conditions are satisfied. But we can use what we can visualize to reasonably make the approximation. Okay, so you can see for the strong motion portion, you can model it as stationary. And then possibly this portion can be regarded as ergodic, okay, because all possible states are visited. Is that clear? Okay. So next, we look at the Gaussian process. A Gaussian process is related to normal distribution. Okay, so at any time, the values are normally distributed. Okay, so an important random process is Gaussian process. We don't call it a normal process, it's called a Gaussian process. Okay, so Gaussian is related to normal. The probability density function are given by this. We have a mean value and sigma is the standard deviation. Okay, so mu is the mean and the sigma is the standard deviation. This is the first order probability density function, and we can get the second order probability density function. Now you have the correlation between xt1 and xt2. Okay, so that's related to the correlation function, and this rho is the coefficient of correlation. Okay, so it depends on the time. Okay, and then you can extend to the nth order probability density function. Okay, usually it's very difficult to obtain higher order probability density functions, so we don't usually use, but you can write the probability density function. Okay, Gaussian random process is completely characterized by its mean value and covariance function kt1, t2, and this is the covariance function. Okay, as in the normal random variable, we need mean value and sigma. Okay, as long as you know the mean and standard deviation, you know the distribution. This is true for a Gaussian process. We need to know the mean value and the covariance function. This is very important because many physical processes resulting from superimposition of a large number of random factors are often modeled as Gaussian. Okay, now I'll give you a minute to think about in probability 概率论. When can we model a random variable? Or when can we approximate a random variable as a normal random variable. When can we model a random variable as a normal random variable? Okay, now let's answer this question. Many physical processes resulting from the superimposition of a large number of random factors are often modeled as Gaussian. This assumption is a consequence of the central limit theorem, 中心极限定理. Which states that under very general conditions, a random variable that occurs as the sum of many smaller independent random variables, each of which is almost negligible in itself, is approximately Gaussian, whatever the distribution of the component variables are. Okay, so let's review what we did in probability. The central limit theorem. If x bar is the mean of a random sample of size n